Alan, thank you very much, and hello everybody. I hope you'll enjoy this evening's presentation. I offered to do this one because there is a tendency amongst geologists and geographers to assume that everything that you see in the Irish mountains is a result of glaciation. And while it's true that the glacial landforms are dominant, and you can still see evidence of what the ice did, quite a lot has happened since the ice disappeared. Various changes have taken place, and it's those changes, or some of them, I can't deal with all of them, but just some of them, the main ones perhaps, that I want to deal with tonight. So that when you go out in the hills, it's not just the effects of glaciation that you're seeing, it's the effects of other processes on the landscape that have happened since the ice disappeared. So this title slide is, as Helen said, is this Donegal? Well, no, it's not Donegal, I'm afraid, although don't we wish it was. It's a Norwegian photograph, and it's just showing you a glacier that's in retreat, and it's showing you the landscape that is emerging as the ice retreats, and it's on those slopes and on that valley bottom that the changes take place, the changes that I'm going to talk about. Now, before, let me see if I can move on. Click. There we are. I just want to recap on one or 2 points I made last week. I showed this diagram last week, this map, which shows the maximum extent of the ice out to the west of Ireland, the west of Scotland, out to the edge of the continental shelf. And it reached that limit about 27,000 or 25,000 years ago. And it had all gone by about 15,000 years ago. So it took about 10 to 12,000 years for the ice to disappear completely. Although there was a short phase of reglaciation up in the mountains between 12,900 and 11,700 years ago. But since that time, since 11,700, we haven't had any glaciers in Ireland. So the changes that have taken place in the landscape, well, in the high corries, it's been changes over 11,700. In some of the bigger valleys that run out towards the sea or run out towards the lowlands, the ice had gone by 15,000. So there's been a slightly longer period in some areas for the changes to operate, to work. We have some indication of how fast the ice disappeared. I've got some numbers here from Donegal. Sorry to bombard you with numbers, but ages like this are not known over large parts of Ireland. There's only a couple of areas where we've got detailed information. And some years ago, we did some work in Donegal on the rate at which the ice retreated. So about 27,000 or 26,000 years ago, ice was at the edge of the continental shelf off the coast of Donegal, about 90 to 100 kilometers offshore. And that had pulled back or retreated to Bloody Foreland, because the moraine at Bloody Foreland that I mentioned last time is 21,000 years old. There's the small picture of the Bloody Foreland moraine hiding behind Helen, but never mind, you probably saw it last week. So in 5,000 or 6,000 years, the ice had retreated across the continental shelf some 90 to 100 kilometers, a very fast rate of retreat. There is a moraine in the Poison Glen that we've dated to 17,000 years ago, and that's shown down there in the smaller picture. The Poison Glen is about 15 kilometers from the outer coast of Donegal, so the ice had retreated another 15 kilometers in 4,000 years. So it had slowed considerably from the retreat across the continental shelf. And the Poison Glen glacier itself, when it created this moraine 17,000 years ago, was no more than about 2 to 3 kilometers in length. Because if you go 2 to 3 kilometers up valley from here, you would cross the ridge and you'd be going down into the next valley. And if all the ice had gone by 15,000 years ago, as we think it had, then the Poison Glen glacier retreated the last 2 to 3 kilometers. It took 2,000 years. So the rate changed over time and with the particular place in the landscape that the glacier was situated. So when we talk about retreat of ice, it didn't go instantaneously. It took a long time, but the rate of retreat varied over that period of time. So The Irish mountains would have looked something like this. This is a view in the Jotunheim of Norway, where there are still glaciers up in the corries, the cirques, but a lot of the major valleys and some of the hill slopes are bare. There's no ice now, snow in winter, of course, but it's on these slopes that the changes that I'm going to talk about take place. And by looking at a landscape like Norway, we can gain some indication of how quickly some of these changes actually operate. I mentioned rates of retreat a moment ago, and I showed you that picture of Norway. I just want to mention some other rates of retreat of glaciers. Contemporary glaciers in Norway are retreating extremely quickly, as they are in other areas of the world. So this glacier, Storbreen in southern Norway, where I've been for the last number of summers. This is our campsite when we go down here in the valley bottom. This glacier has been monitored. There are historic photographs. There are records from previous times about where the glacier was. And in AD 1750, the glacier extended down to this outer yellow line. The yellow lines here are marking the positions of moraines. That is the position of the glacier in AD 1810, 1870, 1930, 1968, I think. And when this photograph was taken, that's where the glacier's snout was. That's AD 2003. And the glacier is separated into two lobes. When I was last there, the snout of the glacier, well, this lobe was up here. So this was in 2019, and this one was up here. So these glaciers are retreating very, very quickly. A rate of retreat of 2.5 kilometers in 270 years. Much, much quicker than the last glacier that exists in the Poison Glen. And these are the two branches of that glacier that we saw on the previous photograph. They're now well separated, and this is the sort of landscape that they're revealing, and this is where the changes take place that I'm going to talk about. So I just wanted to put that in to give you some indication of the rate at which glaciers can retreat and leave the landscape. So I'm going to talk about some of the changes that have taken place on summits, on slopes, and on the valley floors. Now, most of these changes are natural, but some have been related to human activity. And I'll mention that in relation to the development of peat in the landscape later on. I showed this diagram last week as well. I talked about glacial features in the cirques and in the valleys, but tonight I want to talk about summit areas. I want to mention block fields that occur on many summits, and I want to talk about features that occur on some of the steeper mountain slopes, features that we call rock slope failures, features that we call debris slides, and then I'm going to talk about peat development, which tends to be on the more gentle slopes and in the valleys rather than on the steeper slopes and on the summits, but it can occur at high level as well. So a few words about block fields, first of all, because these are very interesting features. And there's been a change in the ideas about how block fields developed in recent years. It used to be thought that the block fields that you get on the flat mountain surfaces or the gently inclined surfaces like the summit of Muckish here formed after the ice disappeared. As the ice disappeared from the summit was ravaged by very severe frost action, frost processes, and these processes broke up the bedrock and produced the blocks. And that was the idea about block field formation for many years. But in recent years, block fields have been seen to be emerging from beneath glaciers in parts of Scandinavia, in parts of North America. So it's now believed that many block fields may be much, much older. In other words, they're not 15,000 years old, as previously thought. They could have survived periods of glaciation. They could, in fact, be very, very old. And the glaciers have been across these areas, but they haven't destroyed them. They haven't disturbed them. Now, in the case of Muckish, I think this is probably a very old block field. And the reason it wasn't disturbed by the ice or destroyed by the ice is because at high level like this, 2,000 feet above sea level, this is where the glacier ice would have been cold based. Something I mentioned last week. The ice was frozen to the mountaintop. It built up to a considerable thickness, but it didn't move or if it did move, it didn't move very much. It was frozen to the mountaintop. It was cold-based ice. Ice in the valleys, of course, was moving. It was warm-based ice, and that ice was able to move through the valleys and through the cols, but it wasn't able to invade the top of Muckish because the little ice cap that formed here prevented it from doing so. So this block field on Muckish could in fact be very, very old. I don't know how old it is. It could have survived beneath several phases of glaciation. But I don't think it's a recent feature. One of the lines of evidence for saying this could be old and that it could have been preserved beneath the ice is that I have never found, in all my visits to the top of Muckish, I have never found a granite erratic. And yet just to the south of here, we've got the Derivé Mountains, we've got Duish and the ridge leading to Slieve Schnacht, all granite. There is no granite, as far as I'm aware, on the top of Muckish, which suggests it was not invaded by ice from those mountains. That suggests to me that there was a small ice cap on this mountain that prevented invasion by ice from the Derivés. And that ice cap was frozen and didn't destroy this block field. There are other block fields though on Irish mountains. This is in the Sheafries, different type of rock, and the boulders, the blocks are much, much smaller. Now it's possible that this is a younger block field. It's possible that this is one that formed since the last glaciers disappeared. Because this rock is, it's got a greater density of joints in it. It would be somewhat easier for this rock to be broken up by frost action since the ice disappeared. So it's possible in this case that this is a younger block field, and this is one that has formed after the ice. So block fields on these flat-topped or plateau surfaces are pretty common, but certain mountains have a lot of blanket peat on the top, and you don't see block fields unless the peat has been eroded. So in this case, you can see that the peat has been eroded. You can see the scar in the peat behind Francis here. You can see bits of peat in the foreground. If this peat had not been eroded away, we wouldn't have known about that block field. So most mountains, most flat surfaces on mountains will have block field, even though you can't see it. And a couple of areas I can think of where I guess there are fairly extensive block fields would be the summit of Mangerton, which has got very thick peat across the top of it, and on the summits of the Comoras, which are fairly flat, but have quite a lot of peat. So I guess block fields are much more common than we actually see in the landscape. Some may be old, some may be young. We're not entirely certain. We haven't been able to date them in Ireland as yet. So moving on from block fields, I want to now talk about some of the features that occur on the sides of the mountains. And we call these features rock slope failures. They're a type of landslide, or they're a type of mass movement. Now the word landslide, I don't use it very much, or although I might use it a lot this evening because it's a simple word to use, everybody understands what it means, but I like to distinguish between features that are in rock, in the solid rock, and features that are in the superficial materials, in the peat and in the soil. And I'll move on to those and say something about those after I've dealt with this section. So rock slope failures, this block diagram shows 4 types of rock slope failure that are fairly common in mountain areas. We've got in the left, top left here, we've got talus. Most people call this scree, but talus is, I won't say it's the correct name for it, but it's the name that the geologists would use more than scree. So this is material that falls from a cliff, usually falls as smallish particles, some boulder-sized particles as well, and it forms an apron of debris across the mountain slope below the cliff. Fairly common in virtually all mountain areas, although sometimes obscured by vegetation. There's a feature then called a rock avalanche, which is a larger feature, forms by an area of the cliff or the crag collapsing, and as it collapses, it fragments to boulder-sized material that has a long run out. So rock avalanches tend to be tongue-shaped, and they tend to go a long way down the hillside. because a large amount of the crag is collapsing at a particular point in time. There are then also features we call rock slides, where again, large masses of the mountainside sort of subside or founder, but they stay more or less coherent. They don't fragment like the Rock Avalanche does. You could push these back into position, or you could jigsaw them back into position in your mind, not in reality. So they're rock slides. They stay more or less intact, but they move some distance down the hillside. And the fourth type on here is called the rock deformation. These features are a bit subtler than the other three. They consist of low ridges with depressions behind them that run across the hill slopes. And I have to admit, I have never yet found one of these features in Ireland. These are pretty common, these three. Rock deformations, I've not found one in Ireland. I guess they are there, I just haven't found one. They're very common on Scottish mountainsides. So there's no reason why they should be absent from Ireland. So I'm not going to say anything more about those. I'm just going to show some pictures and talk about these three in the next few moments. Now, before we actually go on to look at some of the features, I just want to show you what happens when ice is removed from a landscape. It does depend on the type of rock, I have to admit, but in this case, in this quarry, which is in granite, in the Mourns, we can see the effects of what we call pressure release. When the ice covers the landscape, it exerts a lot of pressure onto the rock below the surface. It actually compresses the crust. And when the ice melts and disappears, that pressure is released and the rock expands, or the term we use is rebound. And in this photograph, you can see the ground surface at the top of the photograph there. That's a sort of gradient of the hillside. And if you look below the soil within this section in the quarry wall, you see numerous joints. And all those joints are running parallel to the ground surface. So pressure release tends to generate a series of joints that run parallel to the ground surface. So if the ground surface is steeper, then the joints in the rock will dip, or they'll be steeper than shown here. So on a steeper slope, it's perhaps easy to imagine that some of these slabs of rock might start to peel off and slide away and create these features we call rock slope failures. If any of you saw the presentation last night on climbing on granite in Lofoten that Johnny Parr did, you would have noticed that they were climbing on granite slabs, and some of the corners and cracks that they were going up were in fact areas where large blocks of granite had fallen away as a result of this pressure release and then rock slope failure. But the slopes they were on were all pretty safe now. They were all pretty stable. Okay, so moving on from that, I said there were three main types that we can find in Ireland of rock slope failure. The first one is talus or scree. And generally, it's assumed that scree is formed because of frost action operating in the crags or the cliff above it. So if this cliff has got lots of joints in it, doesn't matter which way they're dipping, as long as there's lots of joints, water will penetrate those joints, and on freezing, it will force the rock apart. And over time, particles will fall and accumulate on the slope below. Well, that undoubtedly happens, because if you go to certain areas of the world today, in the Alps, for example, and you sit at the bottom of one of these slopes, as the sun comes out and starts melting the ice, in the cracks and joints, you will hear the tinkle of rocks as they fall onto the scree. That may be the case at the present day, but shortly after the ice disappeared, it's likely that this pressure release or this rebound caused a lot of material to fall from these crags. So although this surface scree may be due to frost action, there's a thickness of material below here that we can't see. And we don't know how thick it is, but several meters at least. And some of the material at depth below this surface is likely to have formed soon after the ice disappeared in association with pressure release. So scree slopes owe their origin to two different processes: pressure release and freeze-thaw action. So this is a scree slope on muckish, but most mountains have scree slopes. There are scree slopes in the Mournes. In this case, the scree is on granite rather than quartzite that we had on muckish, but nevertheless formed by essentially the same two processes operating over the time period since the ice disappeared. Okay, I won't say any more about scree. I want to go on to talk about rock avalanches and rock slides. And I want to spend a few moments showing you some photographs of Eroding, because of all the mountains in Ireland, Eroding displays the best examples for rock sliding and rock avalanching. So this is Eroding from the southwest, and it shows here a line across the mountainside. You might just be able to pick it out. And then that line starts to descend as a wide band of rubble there. That area there is a huge rock slide. Now there's a huge mass of Eroding that slipped down, but in doing so, it did not fragment to boulder-sized material. There is a lot of boulder-sized material on the surface, but essentially that is semi-coherent bedrock that has slipped quite a few meters down the hillside and then come to a halt. It's stabilized. Going around this side of Eroding, there is a big ridge of boulders curving around the west side with a big dip or a big depression behind it. This, I think, is a ridge formed entirely of boulders, and I think this is a feature that we can call a rock avalanche that came from the western side of the mountain and accumulated on what is in fact like a ledge or a bench of limestone. There's a thin limestone bench that runs around the foot of Eroding. So we've got a rock slide here, we've got a rock avalanche over here. But there's something else here that seems to have occurred before these two, and that is this feature down here. This ridge of vegetation with scree patches, or what seem to be scree patches on its frontal slope. This is another huge rock avalanche coming down from the mountain. If you put these three areas together and push them back up there, Eroding would be a much more substantial mountain than it is. The next photograph is showing the top of this feature, and it's taken from about there. And it shows that this feature consists of a whole series of ridges. Most of them are covered in vegetation, but there are patches of boulders at quite a few places. So I think this area is essentially a rock avalanche, an area of the mountain that not only collapsed, but disintegrated as it moved down the hill. And it's got these inner ridges that parallel this is the outer ridge that we saw in the other photograph running around here. You can't see the steep front of it, obviously, but within it, you've got all these other ridges. If you go to the top of Eroding and you look down to the northeast, you look down onto another mass of quartzite material, this time with very little vegetation. So it's easy to see the feature. It's easy to see that it's composed essentially of rock fragments. Some are 2 to 3 meters in size, many are much smaller, and it occupies this area between the summit of Eroding and this lower peak over here, Mako. Now this feature is very interesting because it's possible that this feature formed on the top of ice. There may still have been a glacier lurking about in this area when this debris came down. It's on the northeast side of Eroding, so the likelihood is that ice would have lingered longer in this location And this could have come down onto the top of a residual or a dying, decaying glacier. And that might account for its hummocky appearance, because eventually the ice beneath had to melt, and this debris would have been lowered as the ice melted, giving rise to a more hummocky sort of surface. Now, a reason for me saying that this might have come down onto the top of ice is because we know the age of this feature. A few years ago, myself and a colleague, we did some work called Cosmogenic Isotope dating to try and establish the age of this landslide event. We selected three boulders, three sizable boulders that were stable, and we took a small sample of rock from each boulder, about 10 centimeters square, a couple of centimeters thick, and we sent them away to a laboratory for cosmogenic isotope dating. Now, this technique measures the concentration of an isotope in the rock. Now, if we assume that this lump of rock was deep below the surface when the rock avalanche occurred, then this surface that we see here only saw the light of day after the dust had settled, after this boulder came to rest. So the buildup of isotope in this rock surface has all been achieved since the landslide occurred. Now, we did three boulders fairly close together, within 10, 20, 30 meters of each other. And the three ages that we got were fairly consistent. So we know that this landslide, this big rock avalanche on the northeast side of Eroding, occurred 17,700 years ago. And that is why I say it could have come down onto the top of a small glacier. Because if you can remember from a few slides back, I said the glacier in the Poison Glen created a moraine 17,000 years ago. So there was certainly still ice hanging about in the Donegal Mountains between 17 and 18,000 years ago. So that's why I say it's possible that this came down onto a residual glacier, but I have to admit it's speculation. Okay, moving elsewhere in Donegal. I'm not apologizing for showing a lot of pictures of Donegal, but it's one of the areas I go to a lot, so I've obviously got a lot of pictures of Donegal and the features there. Moving on to Slieve League, the view of Slieve League from the car park at Bunglass on the cliff top, very dramatic, steep cliffs. Many people might say, oh, these cliffs have been created because of wave action. Waves cut into the bottom of the cliffs and material falls down. Well, that undoubtedly happens. But this has all been covered by ice in the past, and it's likely that the form of these cliffs is due to huge landslides that took place after the ice disappeared. If that did happen, then all the material that came off this mountain slope is now below the water, and we can't see it. But just over here, I haven't been down to this area at all. I've seen it a number of times, both from the ridge and from this car park. This area to me looks like an area of material that has slid down from up here and stabilized. So this could be a clue to form of the rest of the cliffs. But also, as you set off from this car park to go to the summit of Slieve League, very soon after leaving the car park, the path goes through an area where the ground is very disturbed. There are low crags, there are depressions, there are ridges. Crag, depression, ridge. Several small ridges here. Then here, crag, depression, ridge. This is evidence for slope instability or disturbance. But this part of the mountain has not collapsed and gone down to the sea. But what may have happened here is that this area that you see in the photographs could be part of the mountain that is what we call the residual part of the landslide. This is the bit that did not move very far. It moved a little way and then it stabilized. And a bigger chunk of the mountain over to the right is the bit that descended to the sea and is now below the waves. But again, because we can't see what's below the waves, unless we use some geophysical equipment and go out on a boat. Again, that's speculative to a certain degree. But if you continue along the ridge towards Sleeve League, then there's no doubt that there has been a huge rock avalanche much nearer to the summit. Some of you may know this ridge of Sleeve League, and here there's a short arête that you can scramble up or scramble down. And just before this arête, it doesn't show up very well here, there's quite a depression in the ridge. So you continue along the ridge to this point, then you drop and you cross the ridge to low down. Hold on. You cross the ridge, it's lowered here, and then you scramble up to this summit. To the right of this depression, extending all the way down to the valley, is the debris of a large rock avalanche. You can see how it bulges out here and then runs down to this position. And that rock avalanche has determined, to some extent, the route of this trackway up to Sleeve League. This came down, we did the same technique of cosmogenic dating, and we got 3 ages that show that this happened about 17,000 years ago. A bit more recently than the feature on Eroding, but nevertheless the same general age. And it wouldn't surprise me if when this landslide came down, this corrie here, this cirque, still had a small glacier in it. The glacier hadn't yet completely disappeared. But I don't think the glacier extended down here. This looks to me just as if it's run out down the steep hillside rather than onto ice. But there could have been ice in the corrie at the back. Elsewhere in Donegal, in the valley of Glencolmkill, there is evidence for very large scale rock sliding, shown in this photograph. From the crest of the hill to the valley floor, that entire hillside from left to right has been subjected to rock sliding. You can see various lines up here on the what we might call the unimproved land. These lines represent the top edges of large blocks of mountainside that have slipped down the hill a short way. But this area of improved ground, keep hitting the wrong button. This area of improved ground, the green area, is also showing evidence of rock sliding. There are relatively flat areas. There are steep slopes that are craggy. Flat areas, steep slopes, flat areas. And this is characteristic of a rock slide. As I said before, you've got to have a vivid imagination, but you could actually push all that material back up the hillside and jigsaw it back into position. So when you get these anomalous hillsides, the chances are that there's been some movement in the rock, some large scale movement, and that's happened since the ice disappeared. Because this is down in a valley, we can't say that it was created before the last glaciation, because in this valley, the ice would have been warm based and it would have been quite capable of removing a lot of this material. So this must have happened since the ice disappeared. But with this feature, we don't know exactly when, but I would guess fairly close to the time of ice disappearance. So this could be 15, 16,000 years old. Could be a little younger. Other evidence of rock slope failure. This is on the northern side of Quilca, where a large mass of rock has sort of parted company with the mountainside behind it. It hasn't descended, it hasn't disintegrated, but maybe in the next phase of glaciation, when the glaciers come along, they might give it a nudge and send it crashing down. And on some mountains, this is Aru in Leitrim, parallel to the edge of steep slopes, you sometimes come across distinct trenches like this. Now, it might be thought at first glance this is nothing more than a drainage ditch dug out by a farmer some years ago, but it's not, because a drainage ditch would be unlikely to go down into rock. And here you can just see the rock is exposed. A drainage ditch would probably go no deeper than the depth of the peat or the depth of the soil It certainly wouldn't be excavated into rock. This is what we call a tension gash or a tension crack. And it's opened up because this side of the mountain, this is about 100 to 150 meters wide here, this part of the mountain has started to move away from the rest of the mountain. And that must have happened since the ice disappeared. The ice would have provided support to the mountainside, but when that support was removed, you got this pressure release and you got the mountain moving. Now, just over here, below this steep crag on the same mountain, we've got evidence of large-scale rock sliding. So this mountain shows us evidence of small-scale movement in that trench that we saw back there, and it shows us evidence of large-scale movement. This is a huge mass of rock that has slipped down from up here. It's slipped down and it's tilted backwards slightly, and it's come to rest. But it hasn't fragmented. It hasn't broken up to any great extent. Yes, there's some breakage here. Some blocks have fallen a little further, but the whole mass, again, because it's sort of semi-coherent, could be pushed back into position. And this is characteristic of a large rock slide on an Irish mountain. And if you can see down here behind, I can see Helen and myself on the right-hand side of the picture, but down here on the lower ground, there's another one of these areas of rock sliding. But that area, that material has descended a greater distance down the mountainside. On Akil Island, there's a very interesting feature. Again, a rock slope failure, but it's a feature that hasn't descended to the waves, although other material may have gone before it. But as you walk northeast from the summit of Crochan, you'll come to this area where a trench opens up with a very distinctive outer ridge that is the gap. The trench is possibly 10, 12 meters deep in places. And on the left, this is the piece of the mountain that is parting company with the rest. And further along that ridge, you see this huge flake or buttress that again is separated from the rest of the mountain by this tremendous crack. And my wife Frances is very trusting. I put her in these positions to give some scale. I try and convince her that it's not going to fall, but it will one day. Maybe it needs another glacier to come along and give it a nudge. But because these pieces are still attached to the mountainside, it makes me wonder whether they are just residual lumps of a massive landslide that descended and is now below the waves, and we can't see it. Now, welcome to Bake Off. I just want to try and illustrate some of the processes that have happened with these landslides or rock slope failures by showing you a loaf of bread. I call it the loaf of bread analogy. If you cut a loaf of bread part way down, so one slice is hanging forward, that represents a tension gash. And this material here, this slice may eventually fall forward, it may topple, and it may disintegrate and produce a large rock avalanche. In this photograph, the slice has been cut away completely and it's slumped forwards and it's now attached to the cliff at this point. So this is the rock slide type of feature. You get subsidence, forward movement at the base, and usually this forward movement is on weaker rocks that are underneath. So if you imagine the loaf of bread as a mountain, and these are slices of rock that are peeling away, depending on how they peel and depending on what is underneath the top rocks of the mountain, you'll get a different form of landslide feature on the lower hillside. So I think we'd better move away from the loaf of bread analogy. Okay, so those are landslides or rock slope failures. They're deep into bedrock. They sometimes extend for tens of meters into the rock of the mountain. But we get another type of landslide or another type of mass movement on hillsides, and these are the ones we call debris flows. These just affect the peat and the soil and the glacial sediment that occurs on the hillside. These are features that occur at the present day, every winter, following periods of heavy rainfall. Many mountains experience these debris flows, and they're characterized by a scar or a scarp. Where's my pointer? There it is. A scar or a scarp at the head, a sliding surface across which material is moved, and then downslope of that, you get a spread of debris that may be glacial sediment with lots of boulders in it. It may be peat. It may be a mixture of both things. And these can extend some considerable way down mountainsides, and they can do a lot of damage to structures on the lower slopes. This is one on Bengal, near the head of Killary Harbour. This happened in 2007. And you can see where the feature started from, up here on the mountainside. Very steep slope. There's no peat on this hillside, or very little peat, but quite a substantial thickness of soil, probably glacial sediment that was plastered along the hillside. And that material, in association with excess water, has started to move down the slope. And as it did so, it fanned out, created quite a broad track or trail, and ended up down here following the course of a river. Fortunately, in this case, it didn't reach these houses, but in some cases, features like this have destroyed property, although I don't think anybody's ever been injured or certainly not killed in one of these incidents. Now, if peat is involved, as it sometimes is, because we've got a lot of peat on the hillsides, then this term debris flow is sometimes replaced by one of these terms: bog burst, bog slide, or bog flow. And these are very common. I don't think a year goes by without a number of these occurring on some hillside in some part of Ireland. This is one in the Sperrins. It dates back to, I think it was 1991 when this occurred on a hill called Carntocha. And it started in a small area up here. And the debris, the peat debris, which was saturated with water, it occurred after a period of heavy rainfall, produced this great mass of debris down the hillside, and it went down the river channel as well. So in the area, the source area, at the time, after the event, it looked like this. We see the surface vegetation that was carried along by this saturated peat below, flowing down the hillside. And as this surface material was moved, it started to break up into different sized rafts, some of which were overturned, but most stayed in their original upright position. And again, down here. So you can see the surface of movement here, still with quite a lot of water flowing across it, and the rafts of peat here. And you can see from the side over here, and from where I'm standing, the depth to which this goes. So a large volume of peat has been removed from here, and this surface vegetation has been lowered into that depression that's been created. As I said, this one went a long way down the hillside, and then a lot of the peat continued down in the stream channel. So there's obviously a flood that went from this position here to that position. That's the width of the flood. Maybe a couple of meters here, maybe 3 meters on that side, 4 meters possibly. So six meters width, something like that. And standing up maybe a couple of meters above the present day stream. This material destroyed a number of fences that ran across this area. The farmer told me he'd lost a number of sheep as a result of this, and the local angling club who stock the river further down off the mountain were complaining that a lot of this peaty material had killed the fish, and they paid a lot of money to stock the river for their members. So these debris flows, they're very common. They can cause quite a bit of disruption and damage. Here's another one, fairly small feature. Didn't extend as far as the forest, but if it had, it would have destroyed some of the trees. One thing about these debris flows, they're very marked, they're very prominent when they occur. They're very clear for a year or two, but after that time, it's very difficult to recognize some of them because they do colonize and grow over very quickly. So this is probably about 10 years old, this slide, and that is hardly recognizable at the present day. If you drive up the road towards Muckish Gap and look off to the left, you'd have to look quite closely and carefully to see it. They do sort of blend in after a short period of time. The first of these debris flows I ever saw was in the Antrim Hills in 1981. This occurred. It started on a hillside of a hill called Slievenora. It passed across the road and continued down through the forest. And this, I'm standing on the road, or where the road was, should I say, when I took this photograph. This is a block of tarmac with a white line down the middle that was moved several meters from its original position. And there's another block of tarmac down here that was moved as well in this event. So they can be damaging, they can be disruptive, and they are features that occur with great regularity, and usually each winter, even in summer, if you get a period of very heavy rainfall, you can get a debris flow occurring on a mountainside somewhere. Now, allied to these debris flows are features we call debris cones. And these consist of large volumes of rock that come from a point source, usually a gully, and they fan out from the base of the gully to form a cone or a fan-shaped deposit. And this is one of the largest ones I've ever seen in Ireland. It's on the sides of Muckish, and it's a huge triangular-shaped area of debris. And it comes out from this gully that runs behind this ridge, and the gully cuts back quite a way into the plateau of Muckish. It's all rock material. It's mostly what we would say inactive at the present day. It's got a large area of vegetation. There are still some patches of boulders visible, but these, if you look at them, are quite weathered. So they've been there some considerable time, except for this area up here, the apex of the feature. If you look at the rocks around the apex of the feature, they're quite fresh. They're much paler in color. This indicates that they've been deposited here fairly recently. So this feature, this huge debris cone coming out from the gully, you can see the gully a bit better now, although it goes round the corner to the right, is still bringing material down from the mountain. But most of it is not getting very far down the cone. It's been deposited in this upper apex area. How long this cone has been forming for, I have no idea, but I guess, again, it's a feature that started forming shortly after the ice disappeared, and it's still forming today. So if the ice disappeared from this part of Muckish 15,000 years ago, we've seen 15,000 years of slow, gradual buildup of debris coming out of this vast gully. And a similar feature on the side of Glendalough, a bit smaller, but nevertheless, this cone-shaped or fan-shaped body of material coming down from a very shallow or weakly developed gully. And some obviously, some rockfall from these crags alongside, because these large boulders are more likely to be due to rockfall from the crags, but the smaller stuff on this fan surface is probably brought down by heavy rainfall, washing loose stuff from the crags and depositing it in this fan-shaped form. And there's another one over here behind myself and Helen coming out of a gully on this side of the mountain. So they're quite common features on mountainsides. We call them debris cones because of their shape. And again, they're features that have formed since the ice disappeared. But we don't have dates on a lot of these features, so we can't say exactly when they began forming. We can only make the assumption that they started soon after the ice disappeared. If you're fortunate enough to be able to see inside one of these debris cones, and the best place for seeing inside them is usually at the bottom, if they've sort of impinged on a valley floor and the stream has cut into them, you can sometimes see that they're composed of alternating layers of coarse debris, stony debris, boulders, sand, grit, gravel, etc., like the zone running through here. And during periods when there hasn't been much debris added to the surface, it's given the opportunity for peat to develop. And then at a later stage, more debris has been washed down. So in this photograph, we see several phases down here, quite thin layers of peat, thin layers of gritty material, and then a much thicker zone of debris from the hill slope, a much thicker zone of peat, and then some debris washed over the top of it. So looking inside these features, which we can't often do, but when we can, it's useful to do so, we get an indication of how they've developed over time. Development hasn't been continuous. There have been periods of rapid addition of material. There have then been periods when no material has been added or very little, and peat has been allowed to grow across the surface. Okay, I want to move on now to talk about frost action for a few moments on the mountains. And frost action is manifest at the present day in the form of needle ice. This is a block of needle ice taken out from a topsoil, obviously before it melted. It's called needle ice because if you look closely, you can see it's got a vertical structure to it. They are thin, long, thin crystals of ice welded together. It's like a bunch of needles. That's why it's called needle ice. And this tends to form in association with what we call frost susceptible soils. And it forms just below the surface. And it can have some quite interesting and marked effects on the ground surface if the material in which it grows is of the right sort of caliber. Now on the top of Muckish, you can see the effects of needle ice. I was quite lucky to get this photograph because it was after a fall of snow. The snow was quite thin, but the snow started to disappear from certain areas and it lay for a time in these other areas. And the reason it disappeared from these areas, these bare areas, is because these are slightly elevated, only by a few centimeters above the snowy areas. And the reason these areas are elevated is because they have been subjected to uplift by the growth of needle ice. So needle ice grows just below the surface, and as it grows, it's capable of lifting the surface a few millimeters, perhaps a few centimeters. And over time, it can lead to a prominent elevation of the ground surface. Where you have a pronounced slope, and the slope consists of gravel, then needle ice can produce features that we call sorted stripes. And I've only ever seen sorted stripes in the Comora Mountains. 2 or 3 areas, 2 or 3 patches of bare ground where peat has been eroded show examples of sorted stripes. And these again are due to the growth of needle ice. And as needle ice elevates the ground surface on a slope, the larger particles that are lifted tend to migrate to the side. So you get coarse zones and fine zones. Coarse zones and fine zones. And the needle ice has developed in these finer zones. These are zones of moisture or water penetration and flow down the slope. So when it freezes, you get needle ice forming on these wetter sides. And as it elevates the soil, it causes the larger particles to be pushed or to migrate down into these coarse zones. Problem is with these features, they disappear very quickly in the spring and the summer because sheep walk all over these areas, people walk over them, and the best time to see them is when the mountaintops are free of snow, but you've had maybe a few days of severe frost activity, and that's when they start to stand out. And the other feature associated with needle ice is a feature known as a plowing boulder. Plowing boulders, like this one, are boulders that you get on mountain slopes grassy, vegetated mountain slopes. They're boulders that have moved down the slope slowly, and they've left behind them a groove or a depression. And as they've moved down the slope slowly, they've pushed out the soil to the side, and they've pushed out the soil in front. So the boulder is, if you like, plowing itself into the soil. That's why they're called plowing boulders. These form because in winter, when the temperature drops, the boulder is a good surface. It conducts the lower temperature, the cold, if you like, it conducts it better than the surrounding ground. So the ground below the boulder freezes slightly earlier than the ground round about. And in freezing, it attracts water, or it attracts moisture to the base of the boulder. The moisture moves by capillary action through the soil, and it's attracted to this freezing zone below the boulder. So if you find a plowing boulder on a mountainside in winter, and it's a frosty day, if the boulder is not too big and you lift it, you will find a block of ice beneath the boulder. It may only be a few centimeters thick. It may contain soil particles within it, but you will find that the ground below the boulder is essentially ice. So the boulder rests on ice as the frost develops. As the thaw sets in, then again, the boulder conducts the heat better than the vegetated ground. So the ice below the boulder melts. So you've then got a boulder sitting on soggy soil. And the water has got nowhere to go because the rest of the ground is still frozen. So the boulder's sitting on soggy soil. It's also on a slope. So the boulder tends to slip forward a few centimeters, maybe only a few millimeters. And gradually, over a long period of time, you get a groove or a depression behind the boulder, and you get the soil plowed up in front of the boulder. Now, in some winters, that boulder may not move because the frost may not occur. It may not be severe enough. But in other winters, the boulder may move a few centimeters. But very quickly, the vegetation colonizes the bare patch that the boulder leaves. So you don't really have the evidence behind the boulder for movement. You've just got to take my word for it. Okay, the final thing I want to say about the mountains, and one of the changes that's taken place since glaciers disappeared, is the development of peat. This is the first page of an article that was very kindly published in Irish Mountain Log in the summer of 2019, and it was about blanket peat on mountains. Now, the first photograph, the one you see there, is a bit misleading because it shows you a mountain in the Sperrins with what looks like a complete cover of peat or unbroken vegetation. And that is very rare. Where we've got blanket peat on the mountains, we usually see evidence for extensive dissection, extensive erosion. Blanket peat occurs from lowest levels up to some of the highest summits. This is the western cairn on Galtymore. So it's just below, I think, just below 3,000 feet, this cairn. And here we've got eroding blanket peat. So blanket peat has grown right over this summit ridge at some time in the past. It's now rapidly eroding. On the summit of Meal Ray as well, there's the cairn, we've got blanket peat erosion. So a lot of these gentle summits, rounded summits, have had blanket peat on them, even if they don't have it on today. But in one or two places, we can see the evidence for it because it hasn't completely disappeared. Blanket peat is remarkable because it also occurs right down at sea level. This is a site on Akil Island. This is all seaweed, it's low tide, but at high tide, this peat is now being cut into, it's being eroded by the sea. But for this peat to form at this level, the sea level must have been slightly lower at some time in the past, whenever this peat started accumulating. There are some mountains like Troston in County Antrim that I find rather perplexing. because it's a mountain from which virtually all the blanket peat has disappeared. Now, there was blanket peat here, there must have been, because over here and over here, there are peat hags, residual masses of peat that are 1 to 2 meters high. And it's just inconceivable that that peat did not extend across this summit. And where I'm standing when I took this photograph is on the top of a prehistoric tomb, and it's completely covered in peat. But there's no peat here. I do not know why the peat has disappeared from this mountaintop. All the other mountaintops in County Antrim, this is the highest mountain, so the others are slightly lower. They all contain thick blanket peat. It's eroded in places, partly, but there is no other summit where you've got such an expanse of bare ground. So I don't know what the reason is for the loss of such a vast area of peat from this particular mountain. This is more like the situation on many Irish mountains where you've got thick peat. It shows evidence for severe dissection. These blocks of peat with the vegetation there, these are called peat hags. Maybe these terms aren't used so much in Ireland as in the Pennines of England, but they're called peat hags. And the gullies or the channels between them are known as groughs. And these two terms are from, well, they're believed to have been introduced by Scandinavian settlers in the Pennines, which suggests that when the Scandinavians came in the 9th century and settled up in the Pennines, they were familiar with these features. They'd recognize them from home, and they used the same words to describe the features. So it suggests that some of the peat erosion in the Pennines and therefore in the Wicklows and in other mountain areas of Ireland goes back a long time. Some of it may have started well over 1,000 years ago. And there's some evidence from a couple of lakes, I think one's in Wicklow and one in Donegal, that yes, there's been peat erosion and the peat has been added to lake sediments for at least 1,000 years in one of these sites. And in the other site, peat has been added to the lake sediments for about 3,000 years. So the peat erosion has been going on for a long period of time. In some areas where the peat has been cut for fuel, you see the remains of trees. And this view in Donegal shows you a large number of pine stumps. So the peat has been cut down through its full thickness, and these tree stumps are rooted in the underlying soil, the mineral soil, if you like, that existed before the peat started to develop. And there's a closer view of one of these pine stumps. Pine is quite a tough wood and it survives beneath the peat. There were other trees, of course, in the landscape at the time, particularly birch, but birch is a softer wood. It tends to rot much more rapidly, so you don't get as many birch remains. But people in various parts of Ireland have sampled these trees. They've obtained the age of the tree by radiocarbon dating. They've obtained radiocarbon dates on the basal layers of the blanket peat. And in many places, the radiocarbon dates tell us that the peat, this blanket peat, started forming between about 4,500 and 4,000 years ago. So it's fairly recent. It's a recent addition to the land surface. And most people have to cross this stuff when you go to the mountains. You can't really escape it. So everybody has to become familiar with blanket peat. So when you're crossing an area of blanket peat, just remember that it may be something that wasn't there 5,000 or 6,000 years ago. It's much more recent than that. So the question is, why did blanket peat start accumulating 4,500 or 4,000 years ago? There are two ideas about this. One is that climate changed at that time. It got somewhat wetter. It got a bit cooler. So that led to a greater degree of saturation of the ground surface, and that would have encouraged peat development. The other idea is that early farmers, cut down a lot of the forest to create land for agriculture, and that resulted in more precipitation, more rainfall reaching the surface. and coupled with the primitive agricultural techniques that encouraged peat formation. And it may be that both theories, both ideas are correct to varying degrees in different areas. I mean, in some areas, you can't attribute blanket peat on the top of the Galtes to Neolithic agriculture 4,500 years ago. But you could do that at a low site like this in Donegal. So peat is another material that we have large areas of in the Irish mountains, all formed since the ice disappeared. And finally, a couple of slides just to show you what is below the surface that we don't always think about or we don't always see. But if you do see sections in trackways or riverbanks, you may get an indication of what we call the soil profile. And in this case, we've got a podsolic soil here, so-called, an organic layer below the vegetation, very acidic, and below that, a thin zone of bright orange or bright brown material enriched in iron, and then becoming less brown, less orange as you go down towards what we call the parent material, the material from which the soil has actually developed. This material down here has fallen, so we can ignore that. So this type of soil is known as the podsolic soil, and it's due to excessive leaching and acidity of the soil that is capable of dissolving out iron from minerals and carrying the iron down the profile and depositing it a few centimeters below. So podsolic soils are very common in the Irish mountains. Here's another one, slightly different morphology, slightly different color sequence. We've still got the peaty topsoil, very acidic. Water draining through that is very acidic. In this case, it's created a white or a gray layer, a zone of extreme leaching from which organic material and iron oxide has been removed. And the organic material and the iron oxide have been redeposited a few centimeters below. The black layer is organic material essentially, and just below that, the strong brown orangey colored material is iron oxide. And then that passes down into the soil parent material from which this entire profile is developed. So all these soil types, I'm only showing pictures of podsolic soils because they're very distinctive, have been formed since the ice disappeared. So that's my presentation, just over the hour. And I'll finish by pointing out that this leaflet that I mentioned last week is still available. And a lot of the features that I've mentioned tonight are explained in that leaflet. So thank you again for watching, listening. You can go and get a cup of tea now and a slice of toast. Thank you.